machine learning is that the neuron, which is the basic component of machine learning, has one major problem. And the problem is the number of weight it requires to do its computation. And the number of weight it requires also determine the computational cost of that neuron. Let's say, for instance, you have a neuron that have 1,000 inputs. 1,000 input require 1,000 weight. 1,000 weight is what a single neuron in a network needs, which means that the computer have to calculate all the product of every input multiplied by every weight to that particular neuron to produce an output. Now, if that is what is happening in our biological neuron, it means that our biological neuron is not just passing on a signal. It's not just transmitting a signal, but it's actually doing some pre-processing of input to produce a particular signal. And for it to do a pre-processing and being part of a component of a biological brain, it means that neurons by themselves are a computer within a computer. Now, let's look at a simple symbol of a neuron as we see there. Now, what does this neuron represent in artificial neuron? This represents the input. The X represents the input, and the line that joins the circle, which is the node, the neuron, or we call it the cell of perceptron of the artificial neuron, also have a weight. For every input that is connected to a node, there is a weight. But for people who don't understand what the weight is, a weight is a random number that's generated at start that determine what you adjust, since you cannot touch the data X. In any neural network, you don't touch the data. You don't manipulate the data. So you only manipulate the weight. And the manipulation of the weight is what allows you to adjust how the neuron produce an output, or produce an output closer to what you want by adjusting the weight and also the bias. Now, let's look at the function, the mathematical function for this. Now, a basic algebra function X equal to X multiplied by the weight plus the bias. This is the mathematical function of a neural network. This is the mathematical function of a neural network, where the weight, W is the weight, and X is the data. W is weight, and B is also a randomly generated value, just like the weight. So we call that bias. You understand? So what really happens in a neural network is that every input that comes into the node, it's being processed within the cell of a neuron, and then it produces an output based on this function. And the function, the output, is passed to an activator. An activator is another mathematical function that limits, or that allow the value to remain within a certain limit between 0 and 1. It will not go beyond that. Whatever output this calculation, it will remain within that limit. And that is what an activation function is. And it could be any type of activation function. There are various types of mathematical functions, such as a sigmoid, tan X, or even some ReLU or max, or any other one. There are so many of them. But we are not particular about activation function. We are particular now with the design of a neuron. We want to design a neuron to be efficient and as close as possible to a biological neuron in design, whereby we don't want as much as weight as we have in traditional perceptron. Now, we want to reduce the perceptron to the weight of the perceptron per every node in a network to become one. A single weight, just as you have a single bias for every neuron, you can have a single weight for every every neuron in a network. Now, in order to have that, we first of all have to do some assumption. And the assumption is this. We have to consider X in this case to be S. Instead of having it as the raw data, we will call it a signal. We will call this a signal. We will no longer consider it to be the X. But before we go into detail of how this functions, let's look at what a neurons in a biological brain looks like. Now, a biological brain has a cell and is surrounded with a dendrite. Excuse my diagram. A dendrite, and then you have axion, and then you have synapses. So you have dendrite, and then you have the axion, and then I think this is synapses. Synapses. Now, what we believe is that all the dendrites are the source of input to the neurons in a biological brain. So we can liken it to be the X input, X, 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 X. And this could be from 1 to million of input. This signal may be coming from direct from sensors, or it may be coming from another neurons transmitted to this particular neuron. And what this neuron does is it do its own internal processes to this data X and produce a signal that passes through this transmission line. This transmission line, it passes through this transmission line and then passes and sent to another neuron via the synapse. It connects to another neuron via the synapse. But whatever input you pass to this neuron is converted to a signal strength that is passed on. So what we want to do is that I don't really believe that a neuron have weight per every input, because if it does, that is a lot of computation. And I believe because we have a lot of computation of weight, that is why we require a GPU instead of using CPU to do this computation. Because even though a CPU can do it, but it will take very long, especially depending on the volume or the connection a particular network have. But we want to have the same connection but reduce the number of weight. That is why there is need to redesign a neural network, a neurons or a perceptron in a neural network. So what do we do? How do we go about this? Now, from what you see above here, this diagram here shows the solution to what I'm talking about. Now, traditionally, this should have been a perceptron. But what I am talking about, this is no longer a perceptron. It's just a part, a component part of a perceptron. This diagram you have here is no longer a perceptron itself, but a part component of a perceptron. As you can see in a biological brain, there is a cell section, and there is an axiom, and there is an output. So inside this axiom, something is happening there. Inside this cell, something is happening there, and then the output does what you have to do. Now, how do we now design a perceptron to be as close as possible to this one, doing the same thing and dividing it into that number of places? So what we do is that our diagram here is no longer a complete circuit or a complete node for a perceptron, but this diagram that we have here with the signal X is no longer a perceptron, but this whole thing has become an axiom. This is our axiom. So this is the axiom. This section is the axiom instead of a perceptron, but this is axiom. But then we have to design the cell. The cell comes before the signal cell. So we put a circle here. which represent the cell. And the cell have the input. And the input is x1 and x2. But instead of having weight in the input, none of that. The weight is in the axiom. And the bias is part of the axiom. So the axiom is the one that does the computation. The cell do aggregation of the input and produce a signal strength. That's what the cell does. Aggregation of the input to produce the signal strength. Now, what do I mean by aggregation? Let's look at a simple a table and see how that could work. Now, here is a table. Let's draw a simple table. And we have x1, x2, signal, and let's put some data to represent 0.1, 0.3. Just these are random data. 0.2, 0.5, 0.4, 0.6, 0.3, 0.2. Now, let's sum this up and divide by the number of input. The number of inputs here now is 2. So 0.1 plus 0.3 will be 0.4 divided by 2. That will be 0.2. That is the signal strength. 0.2 is the signal strength. 0.2 plus 0.5 is 0.7 divided by 2. That will be 0.35. That's the signal strength. 0.4 plus 0.6, that will be 10 divided by 2. That will be 5. That would be 1, sorry. 1 divided by 2 will be 0.5. 0.3 plus 0.2, that will be 0.5 divided by 2, that will be 0.25. As you can see here, that the mean value of the input, the signal is directly proportional to the mean value of the input, and it varies according to the mean value of the input. So if that is the case, why not forget about the data itself, which is the S, since we cannot adjust it or anything? Let's tell the axiom to know nothing about it. Axiom has nothing to do with the data. The cell does what it has to do with the data and pass signal to the axiom. So the axiom now have a signal. So the signal strength is what is passed to the axiom. So what the cell does, the cell function, the function of the cell, which is cell signal, equal to the sum of the input x n divided by n. This is the signal strength. This is the function of x. The function x, which determines the cell, is the sum of all the input divided by the number of input that produce the signal cell, as I explained in the table here. So in this instance, it means that we have been able to divide the perceptron into 2 major parts as a biological neuron, where the cell do the aggregation of the data and the axiom do the computation of the signals that pass to it. So you can see that the axiom doesn't care about the input data itself, but more about the signal that comes out from the cell. Because the cell just tell the axiom, here is the signals I'm getting. This is how strong it is. Do something about it. And the axiom produce its own output. This output from the axiom can then be passed to another function, which is the activator. And that activator could be your choice of activator, and then that will produce output. So in the essence, what I'm saying now is that a new design for a neuron should be something like a cell with the input, with the x inputs 1 and 2. We're no longer going to put weight here. We're going to do mean summation of x1 to x2 divided by the number of input, and this gives us the signal strength. The signal strength is passed to an axiom. This is our axiom, And the axiom has a weight and also have bias. And that bias is where you have this function S multiplied by the weight, S multiplied by the weight plus the bias. And this will give you the output Y. And this output Y, you can then pass it to your activation. Now, as you can see, we've been able to produce a neuron that have only one weight, one bias, no longer multiple weight. What is the ramification of this? It means that we have reduced the computation cost. The computation cost has been reduced, and we are now going to deal with what? Only factors, not matrices. We are going to deal with factors in these instances and not matrices, because you are only multiplying signal by the weight of each layer. The same, because every signal will remain the same for every cell of the network, because they are all connected to the same network. But the output from that network, of that neuron on the same network, will vary because their weight varies. Excuse me. So what do we achieve here? We have achieved removing multiple weights and reducing it to one. Now let's draw a network W. Excuse me. Let's draw a network where we have a 2-input network with a 1 output. We have a 2 neuron in the middle layer, and the output layer single neuron. Let's interconnect them as normal. As you can see in this diagram, that we have neurons 1 and neuron 2. Each of them has inputs x1 and x2, both connected, but we are no longer having weight in the input. Each neuron have its own weight within it and the bias within it. Just also the output also have its own weight and bias, but no longer have weight at the input per input. So what does that mean? In a typical traditional neuron network, you will have X number of weight, which is the number of input multiplied by number of neurons. This will we will have had 4 weights here and 2 weights here, which makes 6 weights in total. But in this network, because we are now using this new design of neural network, we are now going to have only 3 weights, 2 hidden weights and 1 weight at the output. This has drastically reduced computational costs. But how it's going to perform is what I'm yet to experiment. But I'm designing a code. Maybe I'll produce a next video where I code it in a language that is most simple language that I know, something like a Visual Basic language. I'll code this in Visual Basic language so that to see how simple this can be. Now, so here is what I have concluded, that a neural network can be reduced to a single way per neuron by making this data a cell that produces a signal strength, and the signal strength is what you deal with and not the data itself. So what you guys think? Make a comment below. Thanks.